Hey guys, so this week we're going to begin a new chapter, which is chapter 5, Equilibrium of a Rigid Body. So you have learned about the concept of equilibrium of a point in earlier chapters, and you have also learned about rigid bodies in chapter 4. Okay, so in this chapter it's actually not that different, except that we are going to develop the equations of equilibrium instead of a point is on a rigid body. Okay, the difference between a point and a rigid body is that rigid bodies have volume. Okay, it has a significant size. So what that does to the equilibrium of the object is that the forces can create moment. So in the equations of equilibrium, which you have seen is fx equals 0 and fy equals 0, we also need to consider the moment equation, because unlike a point which cannot rotate because it's already one dot, it has no size, rigid bodies can rotate if it's subjected to forces. So to do that, we're going to look at the concept of free body diagram, which you have also seen in earlier chapters, free body diagram of a point. So now we're going to apply the same thing for a rigid body. Okay, and combining these two concepts, we're going to solve problems involving rigid body equilibrium. Okay, so in this video, we're going to cover, the first part is conditions for rigid equilibrium. So this is very straightforward. A body will be in equilibrium if the summation of forces acting on it, or Fr for resultant force, equals to 0, and because of the size, we need to also make sure that the summation of moment about point O equals to 0, as shown in this diagram. So if you satisfy these two equations, then you will satisfy equilibrium for the rigid body. Okay, next we're going to look at free body diagrams. However, in this video, I'm going to cover these 3 points first, okay, before we actually start on the procedure to draw the FBD, which will be in the next video. Okay, so let's look at these 3 points. Okay, support reactions are reaction forces that are acting on the rigid body due to the support attached to it. So for example, what is support? You might be wondering. So this is a type of support. Okay, how two different members are being connected. So this beam and this wall are connected using a fixed support. Fixed because it can't move anywhere and it can't rotate anywhere. Okay, so this is one type of support, and then we also have a hinge like this, or a pin. Okay, this is a pin support. So you can imagine that this portion can move, it can rotate about this point. However, it can't move left, right, up, down. It can only rotate about this point. And then this is a rocker, okay, which obviously it can rock, but it can't move up and down. This is a roller support. And this is, of course, cable support. Okay, there are other types of support which I'm going to provide in the full lecture slides. All right, now let's look at the support reactions. What are the forces involved when you have a support? So the rule is that if the support prevents translation of a body, let's pause there. Prevents translation means the support does not allow the body to move. Okay, translation here is movement to the left, to the right, up, down. Right? It just prevents any movement of that sort in any given direction. Then a force will be developed in that direction. Okay, an easy way to understand this is just think of yourself standing on the ground. Okay, so are you able to move through the ground? Obviously not. Is the ground able to move up with you standing on it? Obviously not. So you know that while you are standing on the ground, your weight is acting downwards. But not only that, the ground is also pushing up towards you. It's supporting you. So you can't move downward. Therefore, there is a reaction force from the ground, acting on you. So the same thing is happening here. If a rigid body is not allowed to move because of the support, then a force will be developed in that direction. Okay, so it follows that if a rotation is prevented, then a moment will be exerted. Okay, so translation is related to force and rotation is related to moment. So for an example, we have a roller. This is a type of support, and because of that roller, this member, of course, it can move left and right. It can slide left and right, but it can't move downwards. Okay, so because of that, the roller will create a reaction force onto the beam. Okay, so the force will be like this in the vertical direction. Will there be any moment? No, because you can actually still rotate this member. It's free to be rotated. There's only one reaction force. Another example, you have a pin or a hinge. This is how it looks from the side. This is from the front. So this member, which is being supported by this pin, it cannot move left and right. It cannot move up and down. But what it can do is rotate about the point at the center of the pin. Therefore, you have this force, or more accurately, you have forces acting in the x direction because it can't move left and right. You have a force acting in the y direction because it can't move up and down. So of course, these two forces will create a resultant force. But we'll worry about that later. Okay, right now focus on this. Only two directions. Another example, if you have a fixed support, okay, fixed, that means it can't move and it can't rotate. So you will have all three. You have force in the x direction, you will have force in the y direction, and you will have moment. Okay, so these are very basic examples. So there are 10 types of supports that you are going to look at. Okay, so basically whenever you have a question to answer, you can just look at this information. Right, I've provided them in the full lecture slides. And you can check. For example, if you have a rocker, so you just look for rocker. So for rocker, you have a reaction force which is perpendicular to the surface at the point of contact. So if this is acting at this angle, the force will be at this angle. Only one. And then you can resolve this in x and y. Okay, the same applies for any other forces. So in 2D, you only have two supports that have moment. The rest are only forces in x and y direction. Okay, so you can read this. Next is internal forces. There's a whole chapter for internal forces after this. So here we're just going to see what it means. Both external and internal forces act on a rigid body. For example, let's say we take this as a rigid body. For the free body diagram, internal forces act between particles which are contained within the boundary of the FBD. Therefore, they are not represented. So what we see here, you only see the tension in this cable. Okay, and perhaps if you are aware, there's also the weight of this whole body acting down. But we don't know what are the forces in these two cables. Okay, so that is solved using the concept of internal forces. Okay, now let's look at weight and center of gravity. I think you are very familiar with the concept of weight. Okay, in a rigid body, each particle has a specified weight. So it's impossible to consider every single weight of every single particle. Therefore, the system is represented by a single resultant force known as weight of the body. Okay, we use this every day. And the location of the force, which is the weight, is known as the center of gravity. So where this W is acting on will be the center of the geometry. It depends on how the object is. A sphere and a triangle, for example, will have different center of gravity. Okay, there's a whole chapter dedicated to this topic. So for now, it's enough that you are aware of this. Okay, so we have covered the three parts, support reactions, internal forces, and the weight and center of gravity. In the next video, you're going to start drawing the free body diagram.